So now we're going to compute the standard deviation, sigma of x. And let's remember, for something that has a discrete probability, like these are, remember discrete are counting numbers, although -2 we can kind of think of the absence of -$2. So we're still going to count it as discrete and use our probability distribution formula. So in that formula, we're going to need x squares, and we're going to then need to take that x squares column and multiply it times the p of x column. So I'm going to go ahead and put two new columns here to make our calculations a little easier. So we're going to take the x column and square everything there. So if we square 4,998, that's going to give us 2498,0004. If I do the same thing to 2,998, square it, I will get 8,988,004. And if I square 998, that will give me 996,004. And then if I square -2, I'm going to get 4. Now we're going to take this new column and multiply it times our p of x column, our probabilities. And since they all have the same denominator, let's just multiply this, thinking of it as being over 1 times the numerator. So we will end up over here with 2498,004 over 6,000. And then if we multiply our 8,988,004 times the 1 on top, we're going to get 8,988,004 over 6,000. Now here we'll have to multiply the 996,004 times the 3 on top, which will give us 23,980 over, I'm sorry, looking at the wrong number, 2,988,012 over 6,000. And then finally, if we multiply the 4 that we have in this last row times the 5,995, we're going to have 23,980 over 6,000. Now recall, our formula calls for the sum of the x squared times p of x minus the mean squared. So the sum of the x squared times p of x is going to be adding up this entire column. So if I add up the numerators of these fractions, I end up getting 3,698,000 over 6,000. And if we put that into our calculator and make it a little bit easier, it's 6163.33 if I round to 2 decimal places. All right, now let's recall, though, that's the only the first part of our formula. So the variance, sigma squared, is equal to that amount that I just got, and then I have to subtract off the mean squared. So in this case, our mean is our expected value. We want -0.5 squared. Now, -0.5 squared is really 0.25, so we'll have 6163.33 minus 0.25, and that ends up giving us something about, when I put this into my calculator, it wasn't correct, so let me redo that calculation. That ends up being 6163.08. All right, now, that is the variance, but we want the standard deviation. And as we've always done, standard deviation is always the square root of our variance. So let me insert our little standard deviation formula, our sigma. And if I take the square root of 6163.08, I get 78.505 if I just take it 3 decimal places. Now, that may seem like a huge standard deviation, and it is, but if you think about it, there's people who have lost $2, and then there's people who have won $4,998. There's a whole lot of variance between these people down here and the ones who've won money. All right, so now let's look at 15. An insurance company estimates that the probability that an individual in a particular risk group will survive 1 year is 0.999. Such a person buys a $200,000 life insurance policy. Let C denote how much the company charges for a policy. Let X be the company's net gain. The first thing we want to do is construct a probability distribution of X. All right, so I'm going to make a table. All right, so let's call our outcomes X. And again, we'll call our probabilities P of X. Oops. All right, let's think of the possible outcomes here. All right, so let's think about the company's payout, their net gain. All right, let's suppose that the person dies. If the person dies, the company is out $200,000, but they're not out a total of $200,000 because they are going to get whatever that premium is for that life insurance policy. So they're down $200,000, but they get back whatever that premium amount is for the policy. All right, so then they're going to be getting back the amount of the premium if the person doesn't die. All right, so C is going to be a nice positive value they get. All right, so what's the probability that this first one happens? Well, let's notice the probability someone survives is 0.999. So the probability that they would die is 1 minus 0.999, or 0.001. All right, and the probability that someone lives and has to pay whatever that C is going to be 0.999. All right, so there's our probability distribution. Now we want to compute the expected value, but we really can't do that without knowing what C is. So we're going to assume, and really I should have written C first, we're going to determine what C must be in order for this company to break even. Okay, so let's do what they would need to break even. Well, actually, we are going to compute B. Let's go ahead and think that we're going to take X and we're going to multiply it times 0.001, and then we're going to take the C and multiply it times 0.999. All right, so this is going to look a little bit odd, but let's go ahead and do it. We're going to have negative 200,000, make sure I get enough zeros there, plus C times 0.001, and then we're going to have C times 0.999, well, 0.999C. Now, let's just use a little algebra and simplify this. So if I multiply negative 200,000 times 0.001, that's going to give us negative 200. And then if I multiply 0.001 times C, negative 200, I can't type, that's going to give us 0.001C. And then we still have a 0.999C. And if we add together our C's, we have negative 200 plus, and 0.001C plus 0.999C is going to be 1C. So it's just going to be C. All right, so there's our expected value, negative 200 plus C. And since we don't know what C is in this instance, then we don't really know the true expected value. However, here's the thing. If the company decides to charge $300 per year for this life insurance policy, then C will be 100. So notice we would just plop it in there. If they decide to charge $400, C would be 200 once it's added to negative 200, and so on. All right, so now part C, let's determine what C must be in order for the company to break even. Well, if they're going to break even, that means the expected value would be 0. They're not going to have any gain. So that would be 200 plus C would be equal to 0 if their gain is just nothing. They're just breaking even. Well, if we move our 200 to the other side, we can see that they would need to charge $200 for this life insurance policy in order to break even. All right, so let's go to 16. Determine whether or not x is a binomial random variable. If so, give n and p. If not, explain why. Now, one of the important things we want to remember with a binomial random variable is that every time a trial is performed, its probability is the same. So let's take a look at A. The number of dots on the top of a fair 8-sided die is registered, and that should say, as the die is tossed 4 times. Okay, so we have a number of trials, 4. We're going to toss it 4 times. Every single time, it is the same probability for a number to pop up on the die. Assuming, of course, that it's an evenly distributed die, and we'll assume that it is. So this is a binomial random variable. So yes. Let's look at B. The number of defective light bulbs in a sample of 10 randomly selected bulbs from a manufacturer in which 0.001% of all bulbs are defective. Okay, so again, we have n trials, and every single time we select a bulb, it's going to have a 0.001% chance of being defective. The probability of it being defective is the same every single time we choose a bulb. So the answer is yes. This is a binomial random variable. But let's look at C. The number of black marbles in a sample of 5 marbles drawn randomly without replacement from a box with 30 white marbles and 10 black marbles. Now, let's think about this without replacement. The first time I draw a marble, my chance of getting a black marble is 10 marbles out of 40 in the entire bag. But I'm not going to replace the marbles before drawing the second time, which means that my probability in drawing the second marble will become 9 out of 39 marbles left in the bag. So our probability is not the same with each trial, and therefore this is not a binomial random variable. The probability changes with each draw from I guess it's a box, not a bag, the box. Okay, so let's see. I'm starting to run out of time. Let's see. Yeah, I think we can get 17. So, at least part of it. So we're going to have a binomial random variable with parameters n equals 5 and p equals 0.5. And we're going to use the tables in the book to compute the probabilities indicated. All right, so let me pull up the tables. Okay, so here's our cumulative binomial probability. And let's notice that it tells us, it gives the probability that x is less than or equal to a certain value, which is what we're looking for in this first one. So we had that n was 5, so here's our n is 5. We had that p was 0.5, which means we're going to go over to this column. And x is less than or equal to 2. So if we go to the 2 for x right here, straight over to this column, the answer is 0.5. So we're going to get 0.5. Now, this second one, B, is a little bit more tricky. If it had said x is greater than 2, we could have just simply subtracted this one from 1. But since it says x is greater than or equal to 2, we really need to look at the table, find out what the probability is that x is less than or equal to 1, and subtract that value from 1. So if we go back to our table, same spot but slightly higher. Let me find my table here. So here's the value for 1, and we get 0.1875. We want to subtract that from 1. Where did we go here? This will be 1 minus 0.1875. And I'm running out of time, so I may not have time here before it finishes, but you can do that one quickly in your own calculator. I'll see you on the next video.